students. Today we will be learning lecture number 17 on the topic duality and sensitivity analysis. The title of today's lecture is sensitivity analysis. Till now we have seen what do we mean by duality, its theorems, and what are the relationships between the primal and the dual. So, for today's lecture we will look at the topic of sensitivity analysis. The meaning of sensitivity analysis is that suppose we are given a problem, we are given a linear programming problem and we have obtained its solution by any of the methods that we have studied till now. Now, we want to make a slight change in the initial data of the problem, whether it is in terms of the cost coefficients, whether it is in terms of the right hand side, or whether it is in terms of decision variables or constraints. Then what will be the effect of that slight change in the initial data onto the final optimum solution? So, we will study the various methods, how to analyze, given a problem, how to analyze the effect of small change of the initial data onto the final optimum solution, instead of solving the entire problem all over again. So, the outline of today's lecture is we will look at some of the various possibilities that could exist in terms of the slight change that we are talking about. We will study all this with the help of an example and finally an exercise. So, let us suppose we are given a LPP of this form, that is minimization of Cx subject to Ax less than or equal to b, x greater than or equal to 0, where the C is a matrix of the type C1, C2, Cn, etc. A is a matrix Aij. Similarly, B is the right hand side, that is Bj, B1, B2, Bm, and X is the decision variables x1, x2, xn. So, we are assuming that we have n decision variables and we are having m constraints. Now, sensitivity analysis is the effect of the changes in the input data on the final optimum results. So, basically it means instead of solving the problem all over again, we want to observe what happens if a slight change is made in the initial data. So, what are the various possibilities? Let us study each of them. First of all, suppose there are changes in the values of the cost coefficients, that is the Cj's, the C1, C2, Cn. Secondly, we will study what happens if there are changes in the values of the right hand side, that is the Bj's. Thirdly, we will look at the changes in the values of Aij, that is the coefficients of the constraints. Fourth, we will see what happens if we want to introduce a new variable into the problem. Fifth, we would like to introduce a new constraint into the problem. Sixth, suppose we want to delete a certain variable, we want to see what will be its effect. and seventh is the deletion of some constraint. So, let us look at each of these possibilities separately one by one. We will study with the help of this example. Now, suppose there is a company which plans production on 3 of its products A, B and C. The unit profits on these products are given to be rupees 2, rupees 3 and rupees 1 respectively, and they require 2 resources, labor and material. The company's OR department formulates the following problem for determining the optimum product mix. Let us assume that the variables are x1, x2 and x3. These are the number of units to be produced of the products A, B and C. Now, we want to maximize the profit. So, the profit is Z is equal to twice x1 plus 3x2 plus x3. Why is that so? Because it is given in the problem that the profit of 1 unit of x1 is 2, the profit of 1 unit of x2 is 3 and the profit of 1 unit of x3 is 1. So, overall profit is 2x1 plus 3x2 plus x3. Now, there are 2 constraints, one is for the corresponding to the labor and the second is corresponding to the material. It is given that the labor constraint is 1 upon 3 x1 plus 1 upon 3 x2 plus 1 upon 3 x3 is less than or equal to 1, and the second constraint for the material is 1 upon 3 x1 plus 4 upon 3 x2 plus 7 upon 3 x3 is less than or equal to 3. And of course, the 3 variables x1, x2 and x3 should be greater than or equal to 0. Now, this is the LP model that is given to us. We will solve it with the help of our usual simplex method and record the initial table and the final table in this tableau. So, in the top row, if you look at it, we will write down the entries corresponding to the objective function coefficients, that is 2, 3, 1, 0 and 0. Now, the initial table has the bases x4 and x5, because both the constraints are of the less than equal to type and therefore, we need to add slack variables. So, the bases will be x4 and x5 and their coefficients in the objective function is 0 and 0. The column under x1 will be 1 by 3, 1 by 3. Similarly, column under x2 will be 1 by 3, 4 by 3. Column under x3 will be 1 by 3, 7 by 3 and x4 will be 1, 0, x5 will be 0, 1 and the right hand side is 1, 3, right. As you know that next we need to find out the deviation entries, and since the basis has a 0 coefficient in the objective function. So, therefore, 2 minus 0, 0 multiplied by 1 by 3, 1 by 3 gives you 2, and similarly the other entries, this will come out to be 3 minus 0, 0 multiplied by 1 by 3, 4 by 3, 3, and this entry will be 1 and these are the basic variables. So, the entry will be 0 and the objective function value is z is equal to 0. Why? Because x4 and x5 are not appearing in the objective function. So, this is our initial table. Now, suppose we have performed our simplex method and we have got the optimum solution. The optimum solution to this problem is as follows. The basis is x1 and x2. X1 has the coefficient 1 0, 0 1, minus 1 2, 4 minus 1, minus 1 4 and the right hand side is 1 2. The coefficients of x1 is 2 in the objective function and coefficient of x2 is 3 in the objective function. And let us now calculate the deviation entries. 2 minus 2 3 multiplied by 1 0 is 0. Anyway, this is a basic variable. So, straight away we can put these two entries as 0 and this entry is 1 minus 2 3 multiplied by minus 1 2 which comes out to be minus 3. Similarly, this is minus 5 because it is nothing but 0 minus 2 3 multiplied by 4 minus 1 which comes out to be minus 5 and similarly minus 1. Now, what you find? You find that all the entries in this deviation rows is either 0 or negative and that is means that this is the final optimum solution with an objective function value z is equal to 8. Now, if you watch carefully in this table I have highlighted certain entries. What are those entries? It is this submatrix. This submatrix is 1 by 3, 1 by 3, 1 by 3, 4 by 3 and similarly 4 minus 1, minus 1, 1. Now, why are these entries shown in a different color? Is because 4 minus 1 corresponds to 1 0. So, 4 minus 1 is in the optimum table and 1 0 is in the initial table. Similarly, minus 1 1 is in the final table. This corresponds to 0 1 in the initial table and similarly 1 3 1 3 corresponds to 1 0 in the final table and 1 3 4 3 of the initial table corresponds to 0 1 of the final table. And as you already know that this is nothing but B and this is nothing but B inverse. So, this matrix shown in blue in the initial table is nothing but the inverse of this matrix which is shown in the final table. And this is the way the simplex multipliers are obtained as you have seen in the case of duality. So, now coming to our problem of looking at the sensitivity analysis. Suppose we have a slight change in the initial data. What will happen to the solution? First of all, we will study the variations in the coefficients of the objective function. That is, what was the objective function? Let us go back to the objective function. The objective function was 2, 3, 1, 2x1 plus 3x2 plus x3. Now, we will look at the first case. The case 1 is corresponding to the non-basic variable of the optimum table. So, we will look at the optimum table. What is the optimum table? Here is the optimum table, sorry, here is the optimum table. What is the non-basic variable in the optimum table? This one. This one is the non-basic variable in the optimum table, x3. So, we need to change CB to 2, 3. Suppose it is 2, 3. Then we will calculate the deviation entries corresponding to C3, the third variable C3, and C3 is obtained as C3 bar is equal to C3 minus 2 3 multiplied by minus 1 2. Why is that so? Why is minus 1 2? Let us go back. Here it is, minus 1 2. So, the CB is this vector 2 3 and it has to be multiplied by minus 1 2 in order to calculate this deviation entry. So, what do we have? C3 bar is equal to C3 minus 2 3 multiplied by minus 1 2, and this we get an expression in terms of C3, that is C3 minus 4. If you multiply this, you will get this as minus 4, and therefore, you will get C3 minus 4. Now, as you know that for optimality, C3 bar should be less than or equal to 0. So, C3 bar is now C3 minus 4. That means that this quantity should be less than or equal to 0. That is, C3 should be less than or equal to 4. Therefore, what do we conclude? We conclude that as long as the unit profit on the product number C is less than rupees 4, it is not economical to produce product C, because then this constraint will be violated and it will become greater than 0. Therefore, in order to maintain optimality, C3 should be less than or equal to 4. Now, this was the case when we had made changes in the non-basic variable. Suppose the unit profit on product C is increased to rupees 6. We have seen that it should be less than 4. Suppose it is increased to 6. Then what will happen? Then C3 bar will become plus 2, means it will become greater than 0. And this means that the optimality has been disturbed, because this current product mix is not optimum. This solution is not optimum any longer, because the C3 bar entry has become greater than 0, and as you know that this entry should be less than 0. Therefore, what is the remedy? The remedy is that we have to perform another iteration, and by performing another iteration, this is the optimum table that we get. We get the basis as x1 and x3 and its coefficients in the objective function as 2 and 1. Basis is 1 0, x2 is 1 by 2 1 by 2, x3 is 0 1, x4 is 7 by 2 minus 1 by 2, x5 is minus 1 by 2 1 by 2, and the right hand side is 2 and 1. Of course, you can just make sure that this is the optimum table by observing the entries in the deviation row. And what are these entries? 0 because it is a basic variable, minus 1 because this is obtained by 3 minus 2 1 multiplied by 1 by 2 1 by 2. Again this one is a basic variable, so it is entry is 0. This one is 0 minus 2 1 multiplied by 7 by 2 minus 1 by 2, which comes out to be minus 4, and this entry is 0 minus 2 1 multiplied by minus 1 by 2 1 by 2, which comes out to be minus 2. And these are all either 0 or negative. Hence, this is the optimum solution, and the objective function value, that is the profit, is 10 rupees. So, the new solution that is obtained is x 1 is equal to 2 and x 3 is equal to 1 with a cost of rupees 10. So, what does this mean? This means that if the cost has been changed to rupees 6, then the solution remains no longer optimum and we have to perform another iteration to reach to the optimum solution. Now, let us look at case number 2. This case number 2 corresponds to a change which is made in the basic variable of the optimum table. For example, we want to ask this question: what will be the range on C1 as optimality is maintained or not? Is optimality maintained or not? So, as before, we have to express each of the non-basic variables in terms of the coefficient C1, and what do we get? We get C3 bar is equal to 1 minus C1 3 multiplied by minus 1 2. Why is that so? Because this is the coefficients of the top row multiplied by C1 3, because that is the we have to find out what is this C1, what is this value of the C1, and this is that column under C3, and if you solve this you get C1 minus 5. This means that C1 should be less than equal to 5, because we have to make sure that this entry has to be less than or equal to 0. Similarly, we will calculate C4 bar. What is C4 bar? It is equal to 0 minus C1 3 multiplied by 4 minus 1, and this turns out to be 3 minus 4 C1, and that means C1 is greater than or equal to 3 by 4. Next comes C5 bar. This comes out to be 0 minus C1 3 multiplied by minus 1 1, and this is equal to C1 minus 3. Now, since this has to be less than 0, this means C1 should be less than or equal to 3. Now, these are the 3 conditions that should be satisfied by C1 so that optimality is retained. And if you take the common value of all these 3 conditions, you get this common condition, that is the value of C1 should lie between 3 by 4 and 3. If this condition is satisfied, then automatically all these 3 conditions are satisfied. Therefore, for maintaining optimality, the value of C1 should lie between 3 by 4 and 3. Therefore, we have obtained a condition on C1 so that optimality is maintained. Next comes the case 3. This is corresponding to the basic variables as well as the non-basic variables, and this can be illustrated with the help of this example. Suppose we have a new objective function, that is our new z is x1 plus 4x2 plus 2x3. Now, let us calculate the deviation entries. The deviation row in the optimum table will be C1 bar and C2 bar will both be 0. Our C3 bar will become 2 minus 1 4 multiplied by minus 1 2, which is equal to minus 5, and as you know minus 5 is less than 0. C4 bar is 0 minus 1 4 multiplied by 4 minus 1, which comes out to be 0, and finally C5 bar is equal to 0 minus 1 4 multiplied by minus 1 1, which is equal to minus 3, and that is less than 0. So, what does it mean? This means that all the entries in the deviation rows are either 0 or less than 0. This concludes that optimality is maintained. If this objective function is, if the original objective function is changed to this objective function, then optimality is changed because we have verified all the entries of the deviation row and we have illustrated how each of them is either 0 or less than 0. On the other hand, if it is not optimum any longer, then a new iteration has to be performed. In order to illustrate this, let us take this example. Suppose the original objective function is changed to x1 plus 4x2 plus 10x3. Now, let us look at the deviation entries. What do we find? The deviation entries in the optimum table now are C1 and C2 are both 0, so no problem. C3 bar is 10 minus 1 4 multiplied by minus 1 2, which is equal to 3, and this means that this is greater than 0. Again C4 bar is 0 minus 1 by 4 4 minus 1, which is equal to 0, and finally C5 is 0 minus 1 4 multiplied by minus 1 1, which is equal to minus 3, which is less than 0. Now, what do we observe? We observe all the cases to be either 0 or negative except this entry C3. C3 bar is 3, it is positive. So, this indicates that this is not optimum any longer. Therefore, we have to perform another iteration. Since C3 bar is greater than 0, so one more iteration has to be performed. Let us perform this iteration. Here you are. This was our initial table, right. That is, the basis was x1, x2. The coefficients of the CB were 1, 4. Basis is 1, 0, 0, 1, minus 1, 2, 4, minus 1, minus 1, 1, and the right hand side is 1 and 2. Now, since the entries of the objective function are now 1, 4 and 10 and of course 0, 0. Therefore, the deviation rows will become 0, 0 because they are basic variables, 3, 0, minus 3 and objective function value is 9. We will perform the next iteration by observing these entries in the deviation, and as you can see 3 is the largest. Then we will perform the minimum ratio test. 2 divided by 2 and 1 divided by minus 1 is not allowed. So, only option remains with 2 and therefore, 2 is the pivot. Therefore, this variable x 3 will enter the basis and x 2 will leave the basis. And here it is, in the next iteration we have the new basis as x 1 and x 3, which is shown like this: 1 0 it is the basic variable, 1 by 2 1 by 2, 0 1, 7 by 2 minus 1 by 2, minus 1 by 2 1 by 2 and the right hand side is 2 and 1. Again we will calculate the deviation entries. Of course, we have to make sure that the coefficients of this column are changed. X 1 is as it is 1 and x 3 is 10. So, the deviation entries become 0 because it is a basic variable, minus 3 by 2, 0, 3 by 2, minus 9 by 2 and objective function value is 12. Again, observe this deviation row and you find that this 3 by 2 is the largest, and then we perform the minimum ratio test. Of course, the second one is not allowed because minus 1 by 2 is negative. So, only possibility is 7 by 3. Therefore, the pivot is 7 by 3. This indicates that x 4 is the variable that has to enter the basis and x 1 has the is a variable which has to leave the basis. Therefore, our new basis becomes x 4 and x 3. Of course, their coefficients in the objective function value are 0 and 10, and by applying the elementary row operations we have 2 by 7 minus 1 by 7, 1 by 7, 4 by 7. This is a basic variable x 3. So, it is 0 1, x 4 is 1 0, x 5 is minus 1 by 7 3 by 4 and the right hand side is 4 by 7 and 9 by 7. Let us look at the deviation entries. First one is minus 10 by 7, minus 12 by 7, these are both 0, and minus 15 by 2 with an objective function value as 90 by 7. This indicates that the new optimum solution is x 1 and x 2 is equal to 0, x 3 is equal to 9 by 7, x 4 is equal to 4 by 7 and z is equal to 90 by 7. So, with this example we have seen how if the objective function values are changed such that they do not satisfy optimality, then the problem has to be solved in this way and a new optimum solution is obtained. Now, let us look at the second case, that is variation in the right hand side. Suppose the labor is increased by 1 unit. As you know, the right hand side is nothing but the requirement of the labor and the material. So, let us assume that labor is increased by 1 unit. Therefore, the new right hand side will become 2 for the first constraint. Earlier it was 1, now it has increased by 1. So, 1 plus 1 is 2. So, right hand side now becomes 2 for the first constraint. Now, from the initial and the final table, you observe that what is B bar, small b bar? It is nothing but B inverse B. Let us go back to the initial and the final table. If you look at the initial and the final table, yeah, here it is. You observe that the right hand side can be obtained from the original right hand side by multiplying by B inverse. So, here what is the B right hand side? It is 1 3. Now, so 1 3 if you multiply it by B inverse, that is 4 minus 1 minus 1 1. If you multiply it, then you will get 1 2, that is this one, 1 2, that is the right hand side of the final table. Now, the same thing applies if we have now thought of making a change in this entry 1. Suppose this entry we want to make as 2. So, since this entry is now 2, because 1 plus 1 is 2, so we will multiply this B inverse 4 minus 1 minus 1 1 with 2 3, and we will get the new right hand side of the optimum table. So, let us see this, how this is done. Yes, here it is. In the initial table we found this B bar was nothing but B inverse B, 4 minus 1 minus 1 1, 1 multiplied by 1 by 3 1 3, which came out to be 1 2. Now, if the new right hand side is changed from 1 3 to 2 3, then the new B bar will become B inverse B, which is equal to 4 minus 1 minus 1 1 multiplied by 2 3, and if you solve this, you will get 5 1. Therefore, the new solution is x 1 is equal to 5 and x 2 is equal to 1, and the objective function value is z is equal to 13. So, we want to find out what happens to the range of the variation of a constraint resource such that optimality is maintained. By constraint resource we mean the right hand side. There is a constraint, the labor constraint and its resource. So, what should be the range on this constraint resource? By range we mean the lower and the upper limit. So, for finding out that, suppose extra unit of labor costs rupees 4, because if you employ more labor it will involve some cost, and let us suppose that cost is rupees 4. So, the company poses this question: is it profitable to employ overtime labor? This is the question that is addressed. Is it profitable to employ overtime labor? What is the answer? We have to answer that the company, we have to compare the increased profit by added cost of employing overtime labor. Now, the profit has been increased, but at what cost? The cost is that we had to employ more labor. So, therefore, we will compare both these two quantities. What are the two quantities? First one is the increased cost. What is the increased cost? And we will compare it with the cost of the overtime labor. So, the increased cost is nothing but 13 minus 8, earlier it was 8, now it is 13. So, the difference between 13 and 8 is 5 rupees. However, the cost of the overtime labor is rupees 4. So, what does this indicate? This indicates that it is profitable to employ 1 unit of labor, because the cost of employing a labor is 4, which is less than the increased cost, because the increased cost is 5. Now, this leads to a definition of what is called as a shadow price. Shadow prices are defined as follows: the increased profit, in our case rupees 5, in our previous example, per unit increase of labor availability is called the shadow price for the labor constraint. Now, the shadow prices basically reflect the net changes in the optimum value of Z, that is a profit, per unit of increase on the constraint resource, as long as the variables, as long as the variations in the constraint resource does not change the optimum basis. Therefore, we can define a shadow price corresponding to every constraint. So, for every constraint there is a shadow price. There is a shadow price for the labor constraint, there is a shadow price for the materials constraint. Now, let us find the range of the variation on availability of labor such that optimality is maintained. Now, in order to find the range, let us denote by D the amount of labor availability, and let B star be the new right hand side. Therefore, B star is denoted by D2. D is corresponding to the first availability of labor. So, therefore, we want to see what should be the range on D. Now, as you know, for optimality we have to make sure that B inverse B star is greater than or equal to 0. Therefore, what does this mean? This means that B inverse is nothing but 4 minus 1 minus 1 1 multiplied by D 3, which is equal to 4D minus 3 and 3 minus D. Now, as you know, this should be greater than or equal to 0. In order to make sure that this is greater than or equal to 0, D should be greater than or equal to 3 by 4 and D should be less than or equal to 3. Therefore, the range on D should be that D should lie between 3 by 4 and 3. Of course, the optimum solution will be x1 is equal to 4D minus 3, x2 is equal to 3 minus D and x3 is equal to 0. And of course, the maximum profit is, if you substitute this in our objective function, Z is equal to 2 times 4D minus 3 plus 3 times 3 minus D, which is equal to 5D plus 3. Now, it may be noted that in case B inverse multiplied by B star is less than 0, then the table is no longer optimum and hence another iteration has to be performed. Now, similar analysis can be performed for other constraints as well. Therefore, we have studied what happens if a change is made in the objective function coefficients, and we have studied what happens if there is a change in the right hand side. So, at the end of the lecture, I would like you to solve this question: maximize f is equal to x1 minus x2 plus 2x3 subject to x1 minus x2 plus x3 less than or equal to 4, x1 plus x2 minus x3 less than or equal to 3, twice x1 minus 2x2 plus 3x3 less than or equal to 15, x1, x2, x3 all greater than or equal to 0. Assuming x4, x5, x6 respectively as the slack variables for the 3 constraints, the optimum solution is given in the following table. Now, how that has been obtained is another story. You know how to solve it using the simplex method. So, it is given that this is the solution. The solution is x3, x4, x2, right hand side is 21, 7, 24, x1 is 4, 2, 5, x2 is 0, 0, 1, x3 is 1, 0, 0, x4 is 0, 1, 0, x5 is 2, 1, 3, x6 is 1, 0, 1 and the cost is 18 and these are the deviation entries. Now, the question says carry out the sensitivity analysis for each of the following changes. Number 1, coefficient of x1 in the objective function is changed to 2, that is the first part. Second part is coefficient of x1 becomes C1 is equal to 4 and A11 is equal to 2, A21 is equal to 2 and A31 is equal to 3. Third part is coefficient of x2 and x3 changed to C2 is equal to minus 2, A12 is equal to 2, A22 is equal to 3, A32 is equal to minus 1, C3 is equal to 1, A13 is equal to 3, A23 is equal to minus 2 and A33 is equal to 1. Next part, right hand side vector changes from 4, 3, 15 to 2, 4 and 20 and finally, objective function becomes 3x1 plus x2 plus 5x3. So, each of these parts have to be solved one at a time separately. Thank you.